Hello, today. That was the right one. Okay, thought I was on the wrong problem. As you might be able to tell, I'm a little tired, a little down, but physics waits for no man/woman. We must keep moving forward. And that's what I'll do. So, by special request, we will be doing two problems today, namely 26 and 28. I got 28 down here waiting for us, and we got 26 right here. So, I say we just get right into it. Unless you have something you want to wait for, I'm ready to go. Then I think we will go, because you're not saying anything, and you can't talk to me. You probably don't even exist. So let's get right into this. Okay, so we're going to read the problem, we're going to highlight it. So we got a 10 kilogram block, let me zoom in, actually. 10 kilogram block rests on a table. It's on Earth. Great. Love that. And 0.5 is the coefficient of static friction as shown in figure 4-9. Obviously that's figure 4-9. Someone pushes down a block with a 48 Newton force. What is the maximum horizontal pull that will not move the block? So we want a maximum horizontal pull. There we go. So my favorite thing in the world with these problems is a free body diagram. So let's do that. And we're going to have our contact force up and our gravity down. And what I'll also do is I'll write our constants. So say Fn is equal to 48 newtons, mass is equal to 10 kilograms, and mu sub s, right? Yeah, is equal to 0.5. And from this, relatively simple, because we also have that, wait, oh right, because there's the horizontal pull. It's like, why is there static friction and all? There's horizontal pull, and we have our force to static friction. Okay, so we have our nice little equations. Fn equals mg. That's actually incorrect. We do, I guess it's just, what's the maximum horizontal pull? That will not move the rock. We just calculate Fs. Fs equals mu sub s Fn, and stop. Stop, stop, stop. There's a fatal error here. And I hope you caught it, because, I set you up. I actually did this problem before and I genuinely forgot it, but now this is a stick up. What did we forget here? What did we forget? Well, I actually did the stick up wrong, awkwardly enough. That wasn't supposed to be gravity, that was supposed to be our force. And the whole gist was, remember gravity. You can't forget gravity. But of course, I kind of botched it. That's what the lack of sleep does to a person, I guess. Okay, the point was, don't forget gravity. There should be two forces here. So now let's do this problem again with gravity. We never finished it, but we're still going to do it again. So now we know that on this beautiful, beautiful y-axis, the forces are balanced, essentially. Not essentially, they are. So we can say that Fn is equal to F plus mg. And I'm using F to denote the force downwards, just because I feel like it. Now, we're going to solve for this contact force, and we're going to say that 48 is equal to, 48 plus 10 times 9.8 is equal to our contact force, our normal force, and that is equal to 146 newtons. How beautiful. Now, well, it's just kind of trivial almost. Our force due to static friction is equal to mu sub s contact force, Fn. That is equal to 0.5 times 146, which, get this, is equal to 73 newtons. That is our problem, just done, just like that. And okay, we can actually do a little bit more, just make it nice and pretty. What is the maximum horizontal pull that will not move the block? So we can say, since our, that was bad. Since our force to static friction is equal to 73 newtons, and in order for the block to not move, and then more fanciness, that means f sub x is equal to 0, the force on the x-axis, or the net force on the x-axis. Or actually it would be p in this case, or the force due to p, I'm just going to say f sub p, must be less than fs. And then, therefore, fs, yeah, okay, I did that right. Fs must be greater than, or no, did that wrong. F sub p must be less than 73 newtons. And that is our answer. Forgive my miscalculations, but no, we got there in the end. And that's what matters. And that's our problem. That's our 26. So let's move on to 28. We're gonna do the same thing. We're gonna try to go really fast. Don't want to waste your time. So you're dragging a log weighing 500 newtons along a rough surface. Friction, awesome. Not awesome, but cool. Angle of 30 degrees with the ground. With the ground's kind of important in this case. And we have a static friction between the log and the ground is 0.5. What is the minimum tension? In order for the log to begin to move. So essentially, what we want is we're right at the cusp when. So I'm going to say want. We essentially want a scenario in which f sub x is like just going to be greater than 0. It's like just the conditions that make it work. So that's what we want. Now let us define some variables. So we have what we can write, make it a little easier on ourselves, is say, I don't know, how would I even do this? I guess bulldozer weight is equal to 500 newtons. That's equal to mg. I just want to keep that in mind, that that's mg. We have our force, or coefficient of static friction to be 0.5. Don't have any tensions. We don't know any tensions. And we have some more info that's going to be very useful for my favorite thing in the world, a free body diagram. So this is going to be our log. I'm not going to draw the bulldozer because essentially it doesn't really matter. I'll draw it. Okay, fine. You convinced me. I'll draw it. So we got a bulldozer. This is our bulldozer B and our log L. And we're going to have a very nice cable at an angle of 30 degrees. And so what I was trying to say, and then I just gave in. Our force is here, right? And it's going to be translated to this tension right here in some capacity. And the truth is, we don't care about that force up there. All we care about is this tension. So we don't even need to consider this bulldozer, essentially. We just need the tension it would provide. So we can keep that in mind, but, it doesn't really matter. Okay, so now we're going to draw the log a little, isolated and start drawing the forces on it. So we're going to have our gravity down. Got to remember gravity. We're going to have our contact force up. Now, okay, before that, we'll do our friction, force due to static friction. Or, yeah, we can say force due to static friction. And now we're going to deal with the meat and potatoes of this problem, which is the angle and the tension at that angle. So what we're going to say is we're going to draw a nice little triangle for us. And then I'm not going to go over the lines. I'd be horrible at coloring books. 30 degrees angle. And what we can find is that this would be our sine and this would be our cosine, which is awesome. So for up, we're going to have a t sine 30. And then, I probably should have said 30 degrees here. Doesn't, whatever. Then we'll have our t cosine 30 right here. And hopefully you can see the relations with the triangle. We got our essentially the tension is going up and across, and that's what's represented there. So okay, let's move on with that. Honestly, not loving this positioning, so let's see if I can get a nice move going. Don't wanna, ooh, forgot left the 30 degrees behind. They always say never leave a man behind, but I just did. Kind of feel awful. Whatever. Okay, let us draw our equation. So essentially what we know is that f of x is equal to 0. That's our net force on that. Oh, I meant y. I don't know why I wrote x. F of y is equal to 0. The net force on the y-axis is not moving up nor down. Now, fx is a little more complicated because it's like beginning to move, but it hasn't really moved yet. So essentially, we're going to consider position right before it moves. So f of x is still 0 in this case. Okay, getting a little out of breath because I'm, just getting too wrapped up in this. But yeah, let us persevere. So let's start doing some equations. This is one of my favorite stuff in the entire world. So we're going to say that F sub n, our normal force / contact force, plus T sine 30 is equal to mg. Now, we know that mg is equal to 500 newtons in this case, because this is the weight of the... Oh man, this isn't the bulldozer. Oh man, I'm making some mistakes. That's the weight to the log. Forgive me. And essentially, we're going to make this in terms of Fn, and we're going to write that mg, which is 500, so I'll put it a nice 500 here, minus t sine 30. Wow. So now we got a neat expression for Fn in terms of a constant and RT, which we're eventually going to want to isolate. The reason why I separated Fn is because you know what uses Fn? What's really nice? Well, it's the force due to static friction uses Fn, as we're going to see in 2 seconds. So, as we know, the force on the x-axis is equal to 0. In other words, F sub s, maybe we can I don't know if we should divide these or something. Technically, they are different things. But F sub s is equal to t cosine 30. And then again, it's because 0. You can also write, I'll do this for this sake, Fs minus t cosine 30 is equal to 0. Now, let us think, what is Fs? Well, that's kind of simple. Mu s Fn minus t cosine 30 is equal to 0. Awesome. I'm not loving the colors. I mean, we gotta make everything a little brighter. And that sets the stage for an amazing substitution. What am I seeing here? I'm seeing that we have Fn and we have an Fn. So why don't we substitute them? So we're gonna have a mu. Oh god, that was not even mu. Mu sub s times big. You know what? Going blue right now. 500 minus t sine 30, and then minus t cosine 30. Wow. Okay. And so I realized now, I kind of went through this in my brain a little earlier. I put t cosine 30 minus f sine theta, or oh my god, f sub s, just because eventually it's going to start moving to the right, and that's kind of how I thought about it. I believe this is still going to work. I'd be surprised if it didn't. But yeah, let's see. So I forgot to switch colors actually. Just kind of ignored that if that didn't make sense. Essentially the show shall go on. So now we're going to substitute mu sub s. I'm just going to say 1/2 times this big, gotta change the color. That's this big thing, 500 minus t sine 30, and then minus t cosine 30 equals 0. So now we got a nice distribution, 250 minus 1/2 t sine 30 minus t cosine 30. Now we're going to shift everything, and I'm actually going to think about it as moving both these to the other side. Just get rid of the negative signs. Who likes negative signs? I don't know. And what we're going to get from that is that t cosine 30 plus 1/2 t sine 30 is equal to 250. Hopefully you can follow that. It's not too difficult, but yeah, I mean, I still hope you can follow it. What I'm going to do, for the sake of space, because I kind of wanted to keep this on one page if I could. Oh man, it's horrendous. Let's see if I can shift things around a little bit. Excuse me as I do this. Okay, a little better. We got a little more space to work with. Okay, so now what we do is we factor out our t. I love doing this. One of my favorite things in the world, other than doing hardcore math. And this is equal to 250. And essentially, our expression, I'm going to make a nice little box for it right here. It's also for space. It's 250 over cosine 30 plus 1/2 sine 30. And that's just purely constants. And what we see is that we found our minimum tension. That's just stupendous. So when we actually solve this, we're able to get t is equal to, oh, actually, forget the value I got. Here it is, 224.01 newtons. I will say that the answer key here actually conflicts with that answer, but I mean, pretty sure it's right, in all honesty. I don't see any faults in my logic. Trust me, I am the master at finding my own mistakes. So that's essentially our answer. We could write it nice like last time and say that essentially if we wanted to move, I'm just going to speak this one out loud and maybe do a little scribble. Okay, fine, you twist my arm, I'll do it. So we're going to say that in order, oh God, I don't know what I was doing there. In order for the log to move, t cosine 30 must exceed f sub s. And since, I mean, we already kind of said since, not perfect at this just yet, which implies works fine in this context, that the tension must be, actually, I'm just going to do therefore. Essentially what I would do is like divide by cosine 30, but again, I'm getting a little lazy. So, therefore, T, the tension in the, cable, must be greater than 224.01 newtons. And if I believe that would be correct, because any tension greater than moves it, and that, yeah, that is correct. Okay, so that is our two problems. How long did that go on for? We went on for 18 minutes. 18 minutes, two problems, lots of explanation. Not the worst in the world. Not the greatest either. But let's get real. Physics takes a long time. But it's always really rewarding to do the problem at the end. If I'm going to rate the difficulties of these problems, this one wasn't too bad. This one was a little more difficult, especially because of the angle, but definitely feasible. And in an effort to save your time, I will call it right here. I hope you enjoyed the video and it helped you out. I'll see you next time.